In calculus classes, we often ask students to do a problem like this. Using the epsilon-delta definition of the limit, prove that that limit is equal to that number. So we write this down, because that's the translation of that statement into the definition, and we write a proof out. And the question is, why do we ask students to do this? And the answer is so that they really understand the epsilon-delta definition of the limit. It is, after all, the foundation of all of calculus, so it's probably good to have a good understanding of it, rather than just thinking of a limit as a vague notion of plugging in numbers close to 3 and seeing what you get. So once we finish that problem, we'll have this problem done, we'll have a nice proof of it, but then we might have another problem to do. Have we proven that? No, that requires a separate proof. And then we might get another one, and that requires a separate proof. Or we might get another one, and that requires a separate proof. And at some point we might ask ourselves, is this really the best way of doing mathematics? Do I really prove one little statement at a time? And the answer is no, that's not really how we do mathematics. It might be better to come up with one proof that works for any quadratic polynomial like this. As a matter of fact, maybe we could prove that any polynomial of any given degree n has a limit that you obtain just by plugging in the number. In other words, every polynomial is continuous. How do we prove such a thing? Well, we usually break that up into what are called limit laws. Here's one. We could prove that the limit as x goes to a of x to the n is equal to a to the n for any given a and for any given whole number n. How do we prove such a thing? Well, we prove it like we prove anything else involving a limit. We prove it with the epsilon-delta definition, if we're proving it directly. Once we've proven that, we might prove another limit law that goes like this. The limit of a constant times a function is that constant times the limit of that function. And that, of course, only works if that limit exists, but we could prove that. How do we prove it? Epsilon-delta proof again. And another limit law says that the limit of f plus the limit of f plus g is the limit of f plus the limit of g. Once again, we could write down an epsilon-delta proof of that. Great. Once we have all of those epsilon-delta proofs individually, those individual statements, they can be combined with a short argument to show that the limit of any polynomial is indeed the number that you get simply by plugging in the number. And then that would actually prove this particular problem here. We would get this problem proven from a more general statement. In fact, not only that problem would be done, all of these problems would be done simultaneously. So that's probably the best way of actually doing this. Prove it once and for all for every polynomial. Still, we do ask students to do a problem like this. Why? Well, all those steps required to get this polynomial limit were a little bit long, and maybe if this statement is in fact true, can we prove it? Can we prove it directly? And if we can prove it directly, we get a better sense of the definition.